Welcome to this explainer. Today, we're going to completely transform how you view that mundane, everyday chore of taking out the trash. Think about it for a second. Once your garbage bag leaves the curb, it doesn't just magically disappear. It enters this monumental, globally scaled infrastructure. Or, in a lot of places around the world, a total lack thereof. It's a massive system that actually has profound implications for our survival on this planet. So buckle up, because we are taking a fascinating, slightly terrifying, technical, and philosophical journey into the hidden science of waste disposal, treatment, and energy recovery. All right, let's dive right into what is basically a runaway train scenario. When we look at a forecasted 35-year period, the global human population is expected to grow by about 31%, which puts us at nearly 10 billion people by 2050. But alongside that, global waste generation is projected to grow by 69% over that exact same timeline, skyrocketing to a mind-boggling 3.4 billion tons a year. So waste generation isn't just growing because there are more of us. It's increasing at over twice the rate of human population growth. Our consumption is literally outpacing our very existence. And when that staggering amount of waste has nowhere to go, well, the reality is incredibly grim. Right now, as we speak, 3 billion people worldwide lack access to proper waste disposal facilities. 3 billion. When you don't have an engineered system, waste doesn't just vanish, it festers. Improper or entirely absent waste management leads to an estimated 1 million human deaths every single year. Let that sink in for a moment. Taking out the trash is quite literally a matter of life and death on a global scale. This absolute system failure creates two visceral, overlapping crises. On one front, you've got the explosive, toxic fire hazards that come with open burning. See, biological waste naturally breaks down into highly combustible gases, meaning unregulated dumps frequently just spontaneously catch fire, releasing incredibly hazardous smoke. Then, on the other front, we have this tragic environmental pollution where local ecosystems just crash right into our raw garbage. You have animals foraging in unmanaged open dumps, swallowing plastics and heavy metals, and passing those exact toxins straight back into the food chain. It's a total disaster. And we're not just talking about some isolated, distant landfill out in the middle of nowhere. For billions of people, this is a daily, inescapable public health nightmare. When waste is openly dumped in streets or rivers, it creates severe visual and social pollution. The foul odors of things like hydrogen sulfide and ammonia become this ever-present backdrop to daily life. But more dangerously, it forces people, including kids, to navigate environments that are just teeming with disease vectors. Direct, daily exposure to unmanaged municipal and hazardous waste leads straight to the rapid spread of infectious pathologies. So to really wrap our heads around this, we have to separate these devastating consequences into two distinct buckets. On the environmental side, we aren't just talking about a little litter on the side of the highway. We are talking about severe soil, air, and water pollution driven by incredibly complex chemical reactions. Then, on the public health side, we're seeing everything from physical injuries like stepping on improperly disposed medical needles to acute toxicity from inhaling toxic vapors, all the way to long-term chronic diseases like cancer and waterborne illnesses. Waste essentially attacks us on two fronts simultaneously. A lot of these impacts are driven by two invisible killers, leachate and landfill gas. Now, leachate, think of it as this terrifying toxic garbage tea. It's just natural water combining with the moisture of the waste itself, and as it flows, it extracts dissolved toxic metal ions and pathogens. This creates a highly persistent poison that seeps directly into our groundwater. Meanwhile, you've got landfill gas, which forms as organic matter biodegrades. It's a highly explosive mixture packed with methane, and get this, methane is 30 times more potent for global warming than carbon dioxide. Okay, so how exactly did we arrive at this crisis? Well, we kind of have to look back. Way back in 6000 BC, during the Neolithic agricultural revolution, humans finally settled down, and boom, the very concept of waste was born. For thousands of years, it wasn't a huge deal, but hit the 18th century Industrial Revolution, and massive, rapid urbanization turned open dumping into an absolute crisis. It actually wasn't until 1875 with the UK Public Health Act that waste collection even became a legal duty. And shockingly, the world's very first sanitary landfill wasn't built until 1937 in Fresno, California. This is an incredibly new science, all things considered. But as our populations surge and our consumption skyrockets at this completely unprecedented pace, we really have to ask ourselves, what exactly happens when these giant engineered holes in the ground simply run out of room? A sanitary landfill is basically the best option we have among a list of terrible alternatives, but we are producing way too much trash for the Earth to just keep holding on to it like this.
The hard truth is, landfills are not a permanent solution because they are inherently flawed. For starters, every single landfill has a finite service life. You literally cannot operate one forever. They also eat up massive amounts of land, which makes them fundamentally unsustainable. But the most crucial issue here is transgenerational justice. By just burying our waste, we are effectively entombing a toxic legacy. We're leaving a mess that will require monitoring and environmental protection long after we are gone.
Because of that, the modern engineering paradigm has completely shifted. We're moving away from mere disposal to a really sophisticated three-step sequence. Before anything even touches the ground, we have step 1, treatment, which is all about decreasing the waste's capacity to cause harm. Then there's step 2, transformation. Here we apply physical, chemical, or biological changes to drastically shrink the actual volume of the waste. And finally, step 3, energy recovery, where we actively convert that waste mass into usable mechanical, thermal, or chemical energy. This is how we actually fight back. One of the absolute coolest, most advanced applications of those steps is the bioreactor. Imagine these massive, heavily controlled biological treatment tanks. Inside, operators precisely inject specific liquids and nutrients to rapidly accelerate bacterial decomposition. So instead of just burying trash and waiting decades for it to rot, the process is actively managed in real time. It's incredibly complex, super expensive, and requires such immense technical knowledge that, right now, only a handful of countries in the world, places like the US, Canada, and Australia, are able to operate them effectively. Now contrast that slow biological process with intense thermal treatment. Inside an incineration chamber, waste is combusted at mind-blowingly high temperatures, right in the presence of oxygen. This oxidation process achieves a physical transformation. It instantly obliterates the immense volume of the waste while simultaneously neutralizing all those harmful constituents. But the best part? It allows us to recover immense amounts of thermal energy. We are literally pulling power right out of the garbage itself. But wait. There is an absolutely critical takeaway we must understand from all this engineering. A single machine is not the answer. You can't just go out, buy a multi-million-dollar incinerator or a giant biological composter, plug it in, and magically solve a city's waste crisis. It doesn't work like that. Those isolated pieces of technology will completely fail without a comprehensive, integrated system surrounding them. The real secret sauce to making this all work is integration. Notice how the actual treatment phase, like those high-tech incinerators and digesters we just talked about, is really only the middle step of the journey. Upstream, you have to sort the waste. If you don't segregate the organics from the hazardous stuff right at the source, your input is contaminated, and that multi-million-dollar facility breaks down. Then, downstream, treatment always produces some emissions and toxic ash residues. If your downstream emission management fails, you're just creating secondary pollution. Simply put, quality in strictly dictates quality out. There's a quote from our source material that just hits the nail on the head. A treatment technique tells you what is done, but a treatment process tells you how the whole system behaves. We really have to stop looking at waste management as just shopping for a cool new piece of technology. Real decision-making means evaluating this complete life cycle flow. It means bringing together economists, social scientists, and environmental monitors to figure out how our communities actually function, from the moment the bag hits the curb all the way to the final ash. Ultimately, exploring these monumental, hidden systems leaves us with a pretty heavy philosophical challenge regarding our own daily footprint. We have to ask ourselves, is it transgenerationally just to abandon our complex, toxic waste for our grandchildren to solve? Or are we going to step up, commit to the upstream sorting, embrace the advanced processing, and make the massive financial investments required to deal with our own mess today? Thank you so much for joining me on this explainer. I bet you'll never look at taking out the trash the same way again.